And I hear nothing. Maybe they cannot answer. Oh, they say yes in the chat. Wonderful. Yeah, please continue using the chat. I can kind of see it. Maybe you can help me if there's something important. Just let me know. Yeah. We have 2 minutes and then we start. Yeah, who did? Hmm? Yeah, it is recording. It is recording. So welcome everybody. So as you can see on this little screen, I'm now in the seminar room. So if anybody is in Toronto, on Thursday, I will be here also in the seminar room, so you can come in person and do this. And I also hooked up to a different microphone, so I'm not quite sure how the voice is, but it's probably fine. Could you close the door? They're quite noisy, yeah. No, no, no. They know all this stuff. So yeah. So before I start, though, I want to get my list together with those people who want to take it for credit. So who wants to take it for credit again? Can you just put a yes in the chat? So the first yeses were already there, exactly. So who else wants to take it for credit? I think last time we had 2. Now we're down to 1, but that's okay. That's okay. All right. I'm gonna ask this question later again. Maybe not everybody has signed in just yet. But that's okay. Good. So then what do I want to do today? Oh yeah, today is a mathy day. So I told you earlier that my purpose in this class is to focus a little bit more on the mathematics and not so much. So it's not a statistics course, it's not a computer science course. It's really a math course, and I want to see, or I want to teach how mathematics can be used to better understand cancer and cancer growth. And here now I have a little model which I'll show you in a second on oncolytic viral therapy. And in the very simplest form, it can be formulated as a predator-prey model. And then once I have this written down, I want to go through the standard analysis techniques, something like linearization, looking at steady states, looking at their spiral or nodes or stable or unstable, looking at Lyapunov functions, and maybe come all the way to the Poincaré-Bendixson theory. So for me, this is a review of dynamical system theory, which I think is a very important toolbox in this. And so to the people here and the audience online, I will ask lots of questions as we go. And I hope you are up to it and participate. So, all right, so this would be in my numeration 1.7. And I don't like red, so let's use black. Okay, so I call this, it's still red. Come on. A review of dynamical systems. For an oncolytic virus model. Yeah, first, you might know I wanted to do this on the board, but I think actually the projection with this tablet here is easier. And then I have a PDF file which I can upload and everybody can see it. So that's nice. Now, oncolytic viruses. I don't know if you have heard about this or thought about this at all. So the idea is to use a virus to treat cancer. And where does this idea come from? Where this idea comes from the observation that, for example, people who have herpes or herpes sometimes affects the cancer and prevents cancer from growing so much as it would in patients who do not have herpes. So a virus also attacks the tumor cells. And then in oncolytic viral therapy, you are trying to find viruses which target tumor cells and particularly attack tumor cells. Okay. And so here the simplest model, then I have two compartments, X of t, which is the cancer density, and then Y of t are is the oncolytic virus. So maybe concentration of virus particles. And then I just write down a simple model, which I then explain in a second. So X dot is AX minus BXY. And then Y dot equals minus DY plus CXY. Okay, and I call this model 1. So here's the question, how do we get the oncolytic virus? Yeah, we culture them, exactly. You can culture them even in human cell lines, right? You can have cell lines in a petri dish, and you can just culture these viruses there. Okay, we're getting a full audience. I love it. Awesome. Welcome, everybody. So this is the oncolytic virus model I'm going to study now for probably the entire lecture today. It's also called the Lotka-Volterra model, predator prey model. But it fits so nicely for the oncolytic viral therapy, so that I call this the oncolytic viral model. Okay, so what does it do? Just quickly, I don't know how familiar you are with differential equation modeling, or say it the other way. I'm sure some of you are very familiar, and some of you are maybe not so familiar. So it makes sense to talk about the terms just a little bit. Okay, so what is the assumptions here? If it's only the cancer only. So if there's no y in the entire thing, it's only cancer, then we have just the differential equation x dot equals ax. And so this describes exponential growth, right? This is just exponential growth with growth rate a. With rate a. Okay. Now, you could say, or many people would say, a tumor doesn't grow exponentially, it goes into saturation once it reaches carrying capacity. So we should use a logistic term or a Gompertzian term, as we discussed last lecture too. And of course, we should, and we will, and we do that later. But for now, I keep it as simple as I can. So exponential growth, which certainly captures the initial phase of the tumor when it's far away from the carrying capacity. Okay. Secondly, so the virus only. So if there's no cells to infect, right, then the virus will be just washed out exponentially. So this is called exponential decay. Okay, and then the interaction terms are these minus bxy. So minus bxy then is the viral infection term of the cancer cells, right? Viral infection. of cancer cells with the rate V. And then this infection rate or this infection term is proportional to the number of cancer cells and proportional to the number of viruses. So if you have a double amount of virus, you get double the infection. If you double the amount of cancer cells, you also double the infection. And this might not be always true, right? So this there might be a saturation happening. So if the cancer cell number is too large, we cannot just infect them in the same way, etc. So there are other terms possible as well, which we will also study later. Again, here we use the simplest, and this is called a mass action term. And then through the infection by the virus, we lose the cells. So the cells die. So then the cancer cell dies. That's right. Yeah. Okay, so the minus terms are lost terms to the population, then the plus are gained terms. Which then gets us to the plus CXY term. Plus CXY. Here's a different parameter C instead of the B, because from a viral infection of one cell, we might get 1,000 or 3,000 or 10,000 new viral particles. Right, so C is kind of the burst size, and it tells us how many new viral particles we get from one infection event. So C burst size. Actually, to be precise, C over B is the burst size per infection event. And then this term is really, this is C over B times BXY, where the BXY is a term from the first equation, and then you just cancel the B. So then you have this term. Okay, again, this is in the form of mass action, meaning it's just a product of X and Y. And we can look at more complicated interactions, and we maybe do this later again. Right, so allow me to be simple. I think everybody is happy with simple. Okay. So now comes B. So somewhere was A. Where is A in my notes? A is the model. So then, let's say you are a graduate student at your home university, and your supervisor gives you this model. What would you do? What is the first thing you do? Say it again. Find the steady states. Yoo-hoo! Let's find the steady states. That's good. Okay. So I call this equilibria. Equilibria and steady states is the same, right? Existence of solutions. Oh, this is an interesting question too. Okay, let's lose one sentence about this. Existence is clear. Why? So Patrick was asking about existence of solution to problem number one. I say it's clear. Why is it clear? Who knows the right argument? Online people? Where's my chat? Fill my chat with stuff. Okay, zero solution is about the steady state. Yeah, right, with the function, which continuity? What kind of continuity is the right answer? Lipschitz, right? So that's what we need. The right-hand side is Lipschitz continuous, and we have solutions. These are polynomials in X and Y, so certainly Lipschitz continuous. Since right-hand side is Lipschitz. Continuous. Okay, does somebody know the theorem name which gives us this? Pk is one, and the other one? Say it again? No. Piano is used in the proof, yeah. Picalindula, right? I think it's Picalindula. So. Yeah. So in this section, I will mention a few of these theorems, and if you're not so familiar with them, it makes sense to look them up actually and remind yourself. So equilibria. How do we do equilibria then? Going back to the system, how do we compute equilibria? So time derivatives equal to 0. Yeah. So the x dot 0 and the y dot 0. So let me do that here or on the next slide. Another page. Okay. So then we have 0. Hold on. So then we have 0 equals x times a minus by. I factor out an x right away. And y times minus d plus cx. Okay, so I took the above equations. I set the left-hand side 0, and I factor out an x in the first, and I factor out a y in the second. Because then I see immediately when they are 0, right? And the first one, either x is 0 or y is a divided by b. So let's write this down. So x is 0 or y is, what did I say? A over b. And then from the other one, we get y is 0 or x is something, d over c. Yeah. B divided by c. Okay. So then, and that's it, right? There's no other solutions of this little system there. So then we have two steady states. Or two equilibria. So the first one is 0, 0. And the other one is b divided by c and a divided by b. And then just for short notation, I call this u bar and v bar, which is a little bit shorter notation. And the b is not beautiful, so now the b is better. Okay, awesome. So what do we do then? What do we do next? In the standard analysis.
Let's find some time to chat. Yeah, sure.
Oh, we got a Lindelof on the chat. Very nice. Thank you. Check stability. Yes. Let's check stability. And how do we check stability? I have something here. Jacobian. Yeah, let's compute the Jacobian matrix. So through the linearization. Okay. So Jacobian of what? For the Jacobian, we first need to define the right-hand side. So we write this as a system now. Ax minus bxy and minus dy plus cxy. So now we have a function depending on two variables, a vector valued function depending on two variables. So we can compute the Jacobian matrix, which I call df of xy. So this is a matrix. And how do we compute this? How do we compute the Jacobian? Partial derivatives, yeah. You say it, and online it says it too. So the first
partial
line
derivative of f with respect to x.
by. First line by y is minus bx. The second line by x is cy, and by y is minus d plus cx. Awesome, as easy as that. And then we sub in the steady states. So df is 0, 0. If the y and x's are 0, then we just get a here, and a 0 here and here, and then a minus d here. So then we can easily identify the eigenvalues, which is a and minus d. And what does this mean for the type of solution? A saddle. I got a beautiful saddle from the audience and from the online. So this is a saddle. Excellent. So as I said earlier, for some people this is entirely trivial. For other people it might be relatively new. So so I see value in doing this in detail. Okay, df of d over c, so the other point. Yeah. There's a question in the chat. Do we, and we do assume a and d greater than 0. Yes, we do. And the same for the b and c. Okay. So if we sub in these ratios, what do we get? Let's just see. So if I sub in y here, then I get a minus a, so this is 0. If I sub in x here, I get something like minus bd divided by c. If I sub in y there, I get c a divided by b. And down here, I get another 0. Okay? So now here we cannot just directly look at the eigenvalues. And what I often do is I use the trace determinant formula for the eigenvalues. So let's just review this just quickly. So the trace of that thing, of this df, I don't know. Let's call this w for now. So trace of w would then be 0. And the determinant of w, this time this minus this time this, is plus bd over c times ca over b, and then something cancels, so c goes, so b goes, so this is ad, and then with the above assumption, this is positive. All right, so what do we get? Let's look at the eigenvalues, lambda 1 and 2, and this is trace half plus minus 1/2 root of trace square minus 4 that. Okay, that's a formula I will never forget. That's so important. Although it only works in 2D, okay? So don't use this in 3D. You can only do this in 2D. But then, in our case, trace is 0. Determinant is positive. So we get imaginary values. So we get plus minus. The 4 cancels with the 2 in front. So we get just I times root of AD. So purely imaginary. All right. Okay, so what is this now? A saddle, a node, or what is this?
It is a saddle.
Spiral? It could be a spiral. Inward? Outward?
Spiral. Yeah.
Okay, could be. Anything there? Why can't A, B, C, or D be less than 0? Well, if we have A, B, C less than 0, we change the meaning of the model. So here, right here in the items 1, 2, 3, 4, I gave explicit meaning. Cancer cells grow, virus alone decay. And this defines the sign of the A, B, Cs, and Ds. Mathematically, we can do anything, but then we lose the meaning, right? Then it is no longer an oncolytic virus model. Okay. Yeah, anybody else? Purely imaginary eigenvalues. What does it mean? The spiral, it goes in the right direction, but it's not the right answer. Center, right? They call it center. Yeah. So so this means it's a linear center. But now what does this mean for the nonlinear system? So oh yeah, here I formulate this as a question. So let's do that too. Question. Because this is important. So now for the nonlinear system, so the nonlinear system is the full equation, number 1. What we did with the eigenvalues is we look at the Jacobian. So we linearize, we look at the linear model, and we get a linear center. Now for the nonlinear system, this can be one of 3 things. It can be a center as well, or a stable spiral, or an unstable spiral. Okay, so which is it? Which is it? Okay, before I come to the answer, let me digress to the Hartmann-Grobman theorem. All right. So maybe do this in purple. A little digression. So we need to answer this question, a Hartmann-Grobman theorem. So who knows of people online or in the room, the Hartmann-Grobman theorem? And maybe just say yes. I'm not going to ask you to formulate it here. Just raise your hand or say yes if you know the Hartmann-Grobman theorem, or if you think you know it. Yeah, so a few people know it. Very good. But so this one I'm going to review now. Okay. Yeah, so I start with the definition. And the key concept behind the Hartmann-Grobman theorem is hyperbolic fixed point. So the first definition I write down is hyperbolic fixed point, because those fixed points, you can make the transition from linear to nonlinear. For example, a saddle is hyperbolic. So if you get a linear saddle, you also have a saddle for the nonlinear system. A center, on the other hand, we will find is not hyperbolic. So then this connection is not entirely clear. So let's review all this stuff. So an equilibrium point, let's call this U star, of a smooth dynamical system is hyperbolic okay. If when what is hyperbolic? Who knows the answer? Very good. Yeah. Patrick said it. Non-zero real parts of the eigenvalues. So if all eigenvalues have non-zero real parts, yeah, so a very simple definition. You compute the eigenvalues and look at them. So actually, let's look back, okay? So then for the saddle case here, this one, the real part is A for the first one, and it's minus D for the second one, and we just assume they're non-zero. So this is hyperbolic. And this guy here, right, we only have an imaginary part, so the real part is 0. So these ones are non-hyperbolic. There we have it. There all the problem arises. So second, what we need is a homeomorphism. A homeomorphism. What is a homeomorphism? I would love to do this in a bigger class with 50 people, because now I'm only looking at the same 5 people. But then we have online as well. Yeah, so eigenvalues is real part. Very good. No, homeomorphism, what's that? A bijection. Bijection is part of it. Bijective and both directions are continuous. Yeah, okay. So, yeah, so it's a continuous map with a continuous inverse, with a continuous map. this continuous inverse. So you could say it's a bijection where both directions are continuous. And this is different from injective because injective is not bijection. Yeah. But an injective map can be continuous, for sure. Okay. And then third, I need topological conjugate. So two dynamical systems. Are topological conjugate. Oh, and I want to write them down. Yeah, u dot equals f of u, and v dot equals g of v. So they are called topological conjugate. So if there's a homeomorphism which maps orbits into orbits, if there exists a homeomorphism that maps orbits into orbits. So orbits of the first dynamical system into orbits of the second dynamical system. And since it's invertible, we can also reverse the map and get that, okay? It doesn't say, so what, if you envision these, orbits, they are like lines in phase space and they're mapped to each other, but the time you take to go through these lines might be different between the two dynamical systems. Okay. And then we can do Hartmann-Grobman. Why does it not react to anything? What have I done? It doesn't move anymore. Mutate, annotate solve, insert the page. It doesn't react. See, Blackboard is always better. Now it's all gone. Okay. And here it works. And here it works. And where's my notes? And there, oh, I'm back. Good, okay. Orbits into orbits. So now theorem of Hartmann and Grobman. Which says, yeah, consider a smooth dynamical system. So let's call this u dot equals f of u. For example, if u is a hyperbolic a fixed point, hyperbolic equilibrium, then there exists a neighborhood of this point so which means we look close at the fixed point, and in this neighborhood u dot equals f of u is topological conjugate to its linearization. So such that u dot equals f of u is topological conjugate to its linearization. So linearization is u dot equals df at u star times u. And this is a very strong result, right? It tells you if you have a hyperbolic fixed point, you can look very close, and then it looks like the linearization would look like. So as an example, I can always remember things easier if I plot them out. So let's say the nonlinear system f of u looks maybe like this. So maybe we have a saddle point which is curved a bit. So it goes in and out, and then orbits follow this way or this way. So this could be the situation of the nonlinear model. Then the linear model looks like this. So then these are straight lines, as straight as I can plot them with my pen here. And they give you the essential behavior of the stability of this fixed point. But then it's a linear system, whereas the left one is a nonlinear system. But if you look close, they look the same. So here's a question about a center manifold analysis. Very good question. So if you have a center manifold, then you have a non-hyperbolic fixed point because you have eigenvalues equal to 0. And so then Hartmann-Grobman fails. And so we need to do some other things, as we need to do in our case here anyways. Okay. Yeah, before I come back to this, there are a few more thoughts here. A few more definitions. So one is structurally stable. So let's just go into structurally stable for 3 sentences, and then I come back. Okay. So u dot equals f of u is called structurally stable. If each dynamical system which is nearby is topological conjugate. Okay, so then so it has directly to do what we did here before. So I write it in this form. If for each epsilon small, y dot equals f of y plus epsilon g of y is topological conjugate. So I do a small perturbation and I get essentially the same picture. Maybe the lines are curved a little bit different, but essentially we get the same picture. So then this means non-hyperbolic fixed points equilibria are not structurally stable. Okay. Right, so this relates it back to the hyperbolicity of the fixed points. And then one more thought before I continue in our modeling there. If we now have a dynamical system which depends on a parameter, then I can vary the parameter, right? And we all have seen models, let's say mu is a growth rate, so we can up or down. And in a typical situation, it could be that, how do I say this? So let's say if mu is not a critical value mu star, and the system is structurally stable there, structurally stable, but only at mu star it is not structurally stable. But at mu star it is not. Structurally stable. Then we call this a bifurcation value. So then mu star is a bifurcation value. Right, I'm sure you all have heard about bifurcations, like saddle node bifurcation, transcritical bifurcation, Hopf bifurcation, etc. But this gives you a little bit different angle to look at it. So this is then a case, this is a parameter value where orbits nearby are not topological conjugate. So this means the dynamic really changes. You get a switch in stability of fixed points, or you get a periodic orbit showing up, or something really drastically changed. And this can be formulated in the terms of structural stability as well. There's a comment? Oh, there was a different microphone on, okay. Yeah, I cannot hear this then at all. Is any of you logged in? No, right? Okay. That's fine, good. So back to the model that we were looking at. So this would be item C. Back to model 1. Okay, so now we learned a lot. In particular, we learned that the center is not hyperbolic, not structurally stable. We cannot use Hartmann-Koopman, so we need some other ideas. And before I come to the other ideas, maybe let's first look at the null clients. This is some other concept we need to discuss. So the null clients are if you only set one equation to be equal to 0. So then the X null client arises. So we just said X dot is equal to 0. And so we get, yeah, we did this before, right? 0 equals X, A minus BY. So then we have X is 0, or Y equals A divided by B. The same calculation I did before. And the Y null client is the corresponding second equation. So Y dot is 0. So then we have Y is 0, or X was what B over C, C over D, B over C. So I want to plot them now in a phase diagram. So then we plot X and Y, and let's see what information we have. So we have 0 was a saddle, and we can compute the directions. It goes in this way and out this way. And then the null clients are X is 0 and Y is 0. These are the axes. And otherwise, X equals B over C. So maybe this is here. And Y equals A divided by B. So maybe this is here. And then the other fixed point is the point here. And now I'd like to fill this in a little bit with the errors of the phase diagram. So if, let's say if X equals D over C, so I on this line, and Y is small, then the vector field is positive. So then this goes to the right, and here it goes to the left. If X is large, this is, if Y is large, this becomes negative. And similar on the other line, if X is small and Y is A divided by B, then we go down, and then here we go down, and here we go up, and here we go up. You can also just take some points and sub them in and see the sign of the vectors there. But what you see clearly now is this rotating movement right around this fixed point. So it also here looks like a center. So if it maybe completely orbits on. But you might go around like this and like this. And you still don't know if you close the loop, or if you loop inside, or if you loop outside. That's still the question. So then in loop, my question. So how can we decide then? The previous question, stable, unstable spiral, or center? Or center. Okay, back to you guys. How can we decide? Any good ideas? So I did all this with the Hartmann and Grobman for no avail. It doesn't help us anything. But now at least we know why it doesn't help us. But what would help us now? How about a Lyapunov function? What do I see here? Perturbation, and see what happens. Right, and we could definitely do also numerical simulation, right? We could just put it in a computer and numerically simulate and see what happens. But the answer here is a Lyapunov function. So this is in section D. Find a Lyapunov function. Okay, so what is a Lyapunov function? Katarina, you have seen that before? Like a bowl or so, right? And then orbits fall kind of down into the middle. Yeah. Yeah, that's exactly what we want to do. Right. Yeah, so I guess we need a few definitions, right, to do that. So then, oh yeah, so let phi at t and x be the flow of a dynamical system. The flow of a dynamical system. Now I call it x dot equal f of x. So, okay, I switch the notation between u and x. I hope that's okay. Where x is the initial condition, and then phi t of x is the solution. Okay, so x, let's call x0 initial condition, and then phi at t x0 is the corresponding solution. So then, and if we consider x to be, or x0 to be the variable, then we can define this to be a flow, and this is called a flow. Okay. So the omega limit set are those points which are reached in the limit. So as time goes to infinity, we approximate the omega limit set. So then we call this omega at x0 to be all points z in my domain omega, so that there exists a monotone sequence of times, monotonic increasing sequence which goes to infinity. So we go with the time to infinity such that phi of Tn starting at x0 converges to this point. So the omega limit set are all limit points which I can reach if the orbit goes to infinity. So I'm sure many of you have seen omega limit sets before. Let me give you a few examples here. But a typical example would be just a fixed point, and then you have like an orbit coming in, converging to the fixed point. So then this would be the omega limit set. So this would be omega at x0 would be just the fixed point u star. Okay. Or it could be an orbit, where you could have a limit cycle. And then orbits maybe come from outside and they get closer and closer and converge to the limit cycle. Or we can have even more complicated things. We can have a torus, right, where it goes further to the torus. We can have chaotic attractors, which can be omega limit sets in that sense. Yeah, what does this have to do with Lyapunov function? So this gets me a definition, goes on. So let now V is this Lyapunov function. It's a map from phase space into R. The bounded below and differentiable. And then I look at the derivatives along trajectories. So the derivative along orbits is the following. It is given as, I call this v dot. So this is the time derivative d by dt of this new function v, which I evaluate at my flow of the dynamical system. And the flow was called phi. So that's the total derivative there. And of course, I have to do chain rule, right? This is a chain rule. But then phi is a maybe higher dimensional dynamical system, so it's vector valued. So I take the vector valued derivative of v, which is the gradient. So I take the gradient of v, and then times the inner derivative, which is the time derivative of the flow, v dot. Okay. Now, phi dot is a solution of our dynamical system, so it satisfies the differential equation. So then this is gradient of v times this f of p of t and x0. Okay, so then the derivative of this function v along orbits is the same as the gradient of v multiplied to the right-hand side of my differential equation. And this is great because it means we don't need to solve the differential equation. We can just use it. We can just use the right-hand side f and check this condition or compute this relationship here. So now the definition. So v is a weak Lyapunov function. A weak Lyapunov function if this relationship is less or equal to 0. So if v dot is less or equal 0, and with v dot, I mean exactly this v dot I just computed. So gradient v times f is less or equal to 0. And this means that v does not increase along orbits. It stays the same or it decays along orbits. Okay? And a strong Lyapunov function if it's a weak Lyapunov function and another condition, and v dot is equal to 0 only at steady states. So the value for v does not change only on steady states. Otherwise, it would be decay. Right? And so then let's point the picture which you just indicated to me earlier. So a typical situation, let's say omega is a two-dimensional space here. V now depends on two coordinates, x and y. And then typically it's like a bowl. So maybe let's plot a bowl here. So this could be a V. And let's say it's a strong Lyapunov function. Then it would decay until it reaches a steady state. Maybe in what color is this anyways? So then orbits, they go down. Maybe they doodle around just a little bit. But then they end up at the minimum here, which would be a steady state. So this is how a Lyapunov function works. You always go down until you end up where there's no more down. So you end up in a minimum. So let's formulate this in mathematical terms as a theorem. Insert new. And this is the theorem of . And the steady state should be part of the omega limit set. Very good point. Yes. And this is a theorem of LaSalle. Theorem of LaSalle says the following. So we assume we have an initial condition in our space omega. Okay, if V is a weak Lyapunov function, then the omega limit set is contained in all points where V is equal to 0, where V dot is equal to 0. And the more interesting case, if V is a strong Lyapunov function, right? So then V dot equals 0 can only happen at equilibrium points. So then omega of x0 is a subset of all steady states or equilibrium points. Let's call them equilibrium. Okay, so yeah. And so if you can characterize the equilibrium points, so maybe in our example we just have 2, then we know for a strong Lyapunov function that we converge to one of them. So it's great. Yeah, because all right, so let's do that. Let's find a Lyapunov function for our oncolytic virus model. I did so much theory now, I think we forgot everything about our model. But, so let's do this. So this would be then E, find a Lyapunov. So how do you do this? Again, question to the audience. How do we actually find the Lyapunov function? So now your supervisor told you, you find the Lyapunov function by tomorrow at 11. So what would you do? Yeah, there are only 2 ways. So there's no general way to do that. The 2 ways is you look in the literature and maybe some other person has done it and and copy it from there, or you just try. You just try, okay? Try and error. And so here I tell you a mixture of both. So I tell you how to try, but I found this in a different book. So so I did, in the end, I did find it in the literature. I didn't make it up myself. Okay, so one thing you can try for our, now we want a specific for our model 1. So I define a function to be a sum for h of x and y, just to be a function which only depends on x, and another function to only depend on y. So let's call this a naive try. I don't know if it works, which is a lie because I prepared the lecture. I know it works, but I mean, imagine at this point you actually don't know if it works. You just try it out. So just a simple form of this form. Okay, so this h is now the v, right? The h is the v from above here. So what we have to compute here is the v dot along orbits. So then this would be h dot. So then h dot. Yeah, okay, let's be a bit more specific. Sorry. So now along orbits, we need to read this as x of t, y of t. Okay, so x and y are the solution of our differential equation. We sub this into h. So now we can talk about h dot. So then this is d by dt of h of x of t, y of t. All right, and now we're in business and we can do our chain rule thing. So then this is dh by dx times x dot plus dh by dy times y dot. Okay, and now I use my naive idea so that H really is a sum of F and G, where F is only depending on X, G is only depending on Y. So then this becomes F prime X dot plus G prime Y dot, where F prime is the derivative with respect to X, G prime is its derivative with respect to Y. But they only depend on one variable, so I don't need to worry about partial derivatives here. Okay. Now for X dot Y dot, we have differential equations. So let's use them. So then this is F prime times X A minus BY. Okay, plus V prime times Y CX minus B. Okay, so as I just subbed in the right-hand side of my differential equations. And now I would like to try to get H dot equal to 0. So make H dot just identical 0. Let's just see if we can make this work. So this is identical 0 if I have this relation between the F prime and G prime. And this relation I can write in a very smart way. So then I have F prime X divided by Cx minus D is the negative of G prime Y divided by A minus B1. So I write this down here quickly, but now maybe go back in your mind, multiply by Cx minus D, this goes there, and A minus By goes on the other side, and the minus sign comes out because you move the G term to the other side. So I think this is the same equation. But here a miracle happens. What is a miracle? The miracle is that this here only depends on X. And this side only depends on Y. So this is like an idea you might have seen in separation analysis, right? So this depends only on X, this only on Y. So it must be constant. There must be constant, both of them. So both terms must be constant. Hey, this is awesome. This is a really, really strong relationship. One thing I should note here as well, is that X, Y are not the equilibrium points. You remember at equilibrium, X bar was D over C, and then the denominator would be equal to 0. So here we are now not in the equilibrium point. Okay, but then there must be constant. And what is the constant which is not 0? Well, the constant is 1. Choose 1. Again, you can choose 2, or you can choose 5, or you can choose anything. It will always work. But then, of course, we choose just a constant. So then what do we get? From the first one, we then get F prime. So equals 1. And so then we multiply this with Cx over D, and we divide by X. So we get C minus D divided by X. And then for G, we get G prime is, this is also 1. So we get keep a minus sign here. So we have minus A over Y plus B. Okay. And now we can just integrate those, right? So then we get easily F of X is a Cx minus B log X plus a constant C1, and G B of Y is minus A ln Y plus BY plus another constant C2. Well, it seems to go in the right direction. We get something useful. So now let's take these additional constants to be 0. So again, this is a choice. If you don't like to take them 0, you take some other your favorite numbers. It will still work. It's all fine. So we take them to be 0, and then we have something for f, which is this, and we have something for g, which is that. So then we put this back together and we define our h of x and y to be cx minus d ln x plus by minus a ln x. So this is very good. Now, where are we time-wise? Time-wise, it's still time. Okay, so this now satisfies. This is how we found this. So this satisfies h dot is identical to 0. So which means it is a weakly Lyapunov function. Unfortunately, it's not a strong Lyapunov function. I'm so sorry, but maybe we can do better in some maybe later or so. But at least we found a weakly Lyapunov function, so it's not so bad. Now I would like to look to see how this looks like. What actually is this function? This is like a pot. Does this have this typical shape? Can you visualize this function in your head? Can you? Let's get a computer. What is it? Discord? No, it's not Discord. What is it called? Desmos, right? Desmos. Yeah, let's put it in Desmos. Or do it Markey way. Okay. So first of all, h of xy is differentiable. In omega, if we stay away from 0, so from 0 to infinity square, open interval here. Of course, at 0, it is not differentiable because it's unbounded. Yeah. So find the minimum. So does it have a minimum? Well, again, we have these bits. One depends on x, one depends on y. So to find the minimum, we can only look at one of them. So let's look at the f thing. Cx minus e ln x. Okay. F prime, actually, we computed before the c minus d divided by x. And so f prime is equal to 0, or x is equal to, what is it now? D over c, which was our steady state already. Okay. We can do f double prime to see if it's a maximum or minimum. So f double prime then is plus d over x squared, or something like this. So it's positive. So then we have local minimum. Yeah, and then you can look at some limits. So if x goes to 0, then the log goes to minus infinity, with the minus sign goes into plus infinity. If x goes to infinity, then the cx term dominates. So then you can figure out this shape here. So it has a minimum here at d over c. And then here, this asymptotically is minimum and is kind of linear. So that's how the function looks like. And the same will be true for g. G has the same shape, only different parameters. And so then in 2D, we can put it together as well. Who can plot this in 2D? So here's x, here's y, here's h. All right, so in x we have this, and in y we have that. So I always start with the upper circle, and then just draw it like this. And here is exactly the fixed point D over C, and the other one was A over B, B over A. I always forget. A over B, A over B. So this will be the unique minimum in this case for that function. Yeah, but I said it's only a weak Lyapunov function, and we have h dot is equal to 0. So what does this mean? So now we know the shape of h very well, and we know that it does not change, or the level of h does not change on the orbits. So what orbits can we have? Say it again. Say it again. Yeah. Steady state. Oh, steady state, of course. We can have a steady state, yeah. But what if I start somewhere else? So let's make this in red. If I start here, okay, at the red dot, now I know the h level along the orbit does not change. So they need to do what? Yes, yes, exactly. So they are circles. So they go around this h function, but stay on the same level until they come back. So they stay on level curves of the function h. And if I start lower, I get a lower circle. And if I start higher up, I get a higher circle. So let's put this in words. Yeah. That's right. Yeah, that's right. Yeah. I think that's the idea behind it. Yes. So Patrick is asking about Lyapunov stability. And so this would be Lyapunov stable, right? This situation. Yeah. Yeah. So let's put this in words. We have here. What is this? Where's my undo? Where's my undo? So okay. So each solution lies on a level sets of h of xy. So meaning h of xt yt equals some constant. And these are the level sets of this function. Yeah. And yeah, so that's all we need. That's all we need. So we also know actually that h goes to infinity. If we continue further here, it goes to infinity. If we go up here, it goes to infinity. It has a unique minimum, and all bonded orbits surround it. So here's our center. All right, so now we prove that we actually have a center for the nonlinear system proof. Plus. Okay. So this proves that yeah, the fixed point, again, where's my coordinates? D divided by C and A divided by B is a nonlinear center. I'm very sorry for you. You said a spiral earlier, but I give you a spiral in the next lecture. But here we definitely get the center. Very good question. Does this depend on how we choose A? So maybe you come up with another Lyapunov function, which then gives us a, well, yeah, can it give us a different result? It cannot, right? Yeah, it cannot. So you can definitely find a different Lyapunov function for sure, but it would still give us the same result. Yeah. If you multiply f and g by something, it doesn't matter at all. Yeah. Oh, if you do a product form, Very interesting. Yeah. I did not try. I don't know. But sometimes it could work. Yeah. Sometimes you can do it for a conflict. Is this function non-negative? Yes and no. So we found a unique minimum here. Okay. And you remember I had these arbitrary constants C1, C2 here and here. So if my minimum is too small, I can just add something and move it up. Yeah. Good question. Other questions? Why did I say the choice is naive? Maybe it's not naive. Maybe it's smart. I don't know. It's the first idea because I decouple them in this particular way. Yeah, might not work.
The beginning, like you said, this solution was okay only in 2D.
Yes.
But later on, you mentioned the solvents in the complicated case, which is 6D.
Yes.
Then
So yeah. So the Lyapunov function method works in any dimension. So it could also be.
the solution would be the
Um,
initial approach.
Well, with the linearization, you can do all this. The only thing which is only 2D is my trace determinant formula. So the trace determinant formula does not work in high. Yes, sorry. Yeah, so then we use the Routh-Hurwitz conditions. Yeah. Okay, so let me see if this is a good place to stop. So then we did that, and we did that, and
I had another.
yeah.
Is there a component?
so the Lyapunov exponent has a different name, a similar name. But the Lyapunov exponent is used to describe if orbits come together or if orbits separate. And this is also used for the nonlinear system, not for the linear system. And positive Lyapunov exponent means it is sensitive to initial conditions and can lead to chaos. So you might have seen it in that context. Yes, yeah. Yeah, so that's a good place to start. That's the material I wanted to cover for today. So are there any more questions? So we really needed to work hard to find out if this point is a center or not, but we got it done, so that's good. Exactly, yeah. So we need the Lyapunov function there. Yeah. Yeah, if we don't find a Lyapunov function, we need to find something else. Maybe the perturbation methods, which was somebody announced there. So yeah. Oh yeah, my question initially, if there's anybody online who wants to take the course for credit, let me know now. I'll be quiet forever. Good, thank you very much. There's one. Okay, need to catch your name. So I won. I didn't understand. Good reference.